consider two identical and finite isolated system of constant heat capacity C. So we are given two systems which are at temperature T1 and T2, and it's also given that they are finite system, they are not infinite reservoir, and then T1, it's also given that T1 is greater than T2, and in between these two reservoir an engine it's working. Okay, so we are having an engine which is working in between these two reservoir until their temperature become equal, and this is only possible when we will treat the reservoir one this reservoir and this reservoir as a finite bodies. Okay, so we are having a engine which is working between these two finite reservoir, and it's also further it's given that taking into account that work performed by the engine will be maximum if the process is reversible. Okay, so it's given that the process it is reversible. So let's draw the diagram first and then try to understand. So here this when the working substance it undergoes the cyclic process, it will take Q1 amount of energy from this reservoir at temperature T1. Okay, and it will reject Q2 amount of energy to the another reservoir which is at T2, such that T2 is smaller than T1. Okay, and then W is the amount of work done that's performed by this reversible cycle. Okay, and this can be written as W, that is equal to Q1 minus Q2. Okay, and let's assume that if we consider that, let TF be the final temperature. TF be the final temperature. Okay, what is that final temperature? Because when the working substance it undergoes the continuous cyclic process, okay, so every time it will extract Q1 amount of heat from this reservoir. Okay, and it will eject Q2 amount of heat to the lower reservoir, and slowly after some time what will happen that the temperature of the reservoir which was initially at temperature T1, its temperature will reduce to a certain value TF, and the temperature of the reservoir which was initially at temperature T2, its temperature will rise to a final value of the final temperature value which is TF. So when these two reservoir, both of these two reservoir, they are going to at same temperature, then it will no more be possible for the engine to extract heat from the upper reservoir and deliver the some amount of heat to the reservoir, the lower reservoir. Okay, so let's say that Q1 is the total amount of heat which is extracted by the this working substance. Okay, so Q1 will be C, because C heat capacity it's given to us C, and then T1 minus TF, where TF is the final temperature of these two reservoirs which is common to both of these two reservoirs. Let's say this is equation number 1. And then similarly Q2, the heat which is gained by the lower reservoir which is equal to C, and TF minus T2. Okay, now W, the work done performed by the engine, that is equal to Q1 minus Q2, and after substituting the value of Q1 and Q2 from equation 1 and 2, so we will obtain that this is equal to C into T1 plus T2 minus 2 times final temperature. Okay, let's say this is equation 3. So here, in order to maximize, so in the question it's asked that what is the maximum value of the work that can be obtained from this type of situation. Okay, so we have to calculate the value of TF, what is the final temperature, and to evaluate TF we have to evaluate the corresponding entropy change for the both of the reservoir. Okay, now because the first reservoir, the entropy change for the first reservoir, let's say that is delta S1. Okay, that's the entropy change for the reservoir which is at temperature T1 initially, and its final temperature become equal to TF. Okay, so that will be C times logarithmic of final temperature divided by the initial temperature of the reservoir which is T1. Okay, let's call this as equation number 4. Now similarly the entropy change for the reservoir 2, that is C ln final temperature divided by initial temperature. This is equation number 5. So for the working substance the entropy change is going to be 0, because the working substance it's going through a cyclic process, and then again from the point from where it started the process, again it will reach at the same point. So the net entropy change during a cyclic process, it's going to be 0. Okay, so there will be no entropy change for the working substance here. So the net entropy change of the universe, delta S, will be delta S1 plus delta S2, and that should be greater than equal to 0. Okay, where equality hold for the reversible process and inequality that's for the irreversible process. So just make a substitution of the value of delta S1 and delta S2 from equation 4 and 5. Okay, so when you do that, so that means this is equal to C ln TF square upon T1 T2, and this should be greater than equal to 0. Now this is equation 6. Okay, now we want to maximize the W here in equation 3. So for that we need the value of TF that should be as small as possible, and that minimum value is determined from this equation here. So okay, so the minimum value of TF is determined when we will equate this delta S, when we equate this to be equal to 0, and that's in fact the result that we should use for the current situation, because it's given that the process it is reversible, it's given here. Okay, so for the reversible process entropy change it's going to be 0. Okay, so that means from here I can write that ln TF square upon T1 T2, that's equal to 0, and this is possible. Let's go to the next page. This is possible only when TF square upon T1 T2, this is equal to unity, or you can say that when TF, this is equal to square root of T1 T2. Okay, so now we have obtained the value of TF, so that means now we can evaluate what is the maximum amount of work done that we can obtain from these two finite reservoirs. Okay, so what was W equal to? So W was equal to C T1 plus T2 minus 2 times TF. So now substitute the value of TF from here. Okay, so this is further equal to C times T1 plus T2 minus 2 under root T1 T2, and this can be further rewritten as C under root T1 minus under root T2 its whole square. Okay, so this is our final answer. So that is the maximum work that we can achieve from such system of two reservoir, which two finite body which are at initial temperature T1 and T2. Okay, so if you take a look at the options, so here the option D, it matches with our answer, so therefore option D is correct here.
A bright dwarf star has volume V and contains n electrons, so that the density of electron is n is equal to n by V. Taking the temperature of the star to be 0 Kelvin, the average energy per electron in star is given by this expression here. Okay, where m is the mass of the electron, the electronic pressure is. So we have to determine what is the pressure exerted by a system of electrons inside the white dwarf. So here, if we treat the electrons as the gas, so that means we can apply the results that we developed in thermodynamics for the case of gas molecules. Okay, so the relationship that we are going to use, that is the first law of thermodynamics, which says that du, that is equal to dq minus dw, or in the modified form this can be written as dq, that is equal to tds minus p dv. So let's call this as equation 1. Okay, so what is given to us, it's the average energy per electron. Okay, so that is E naught, that is equal to 3 h cut square upon 10m multiplied by 3 pi square n and its power 2 by 3. Okay, and small n, basically this is the given to be the number density of the electron. Okay, now the total energy for this system containing n electrons, that is given if we denote that energy by U, and that is equal to the number of electrons multiplied by the average energy per electron, and this turns out to be equal to n multiply by so what I'm doing is I'm curving all the terms here, the constant terms other than the number density in one single constant c. Okay, and then the remaining term which depends upon the volume, that is equal to n divided by v power 2 by 3. Okay, now the pressure can be found from the equation 1. Let's call this as equation 2. Now from equation 1 we can write P, that is equal to minus du by dv by keeping s constant, and also the total number of electrons, that's also going to be constant here. Okay, so now we are going to make use of the equation 2 and 3. So here the only variable is going to be volume B. All the remaining terms, they will be constant. So by making use of equation 2 and 3, we obtain pressure, that is equal to minus sign outside, and then keep the other constant terms outside, n c, and then n power 2 by 3, and then the differential of curly v of v power minus 2 by 3, and that is equal to minus n c n power 2 by 3 multiply by minus 2 by 3, and differential of v, that will give us v power 2 by 3 plus 1. Okay, and this turns out to be equal to 2/3 of n, and then if you further multiply all these terms, the constant terms here, so that they become equal to again this quantity E0. Okay, so that is equal to c multiply by n by b power 2 by 3, and then into 1 by v. So this b, so I have separated this the volume term into b power 2 by 3 and then multiply by 1 by v. So this entire expression, this quantity, this is nothing but this is equal to E0. So we can rewrite this as, that is equal to 2 by 3 and then n by v 0, and that is equal to 2/3 of this quantity. Okay, so that's the final answer. So therefore option D is the correct answer here. Next question is, in the radiation emitted by a black body, the ratio of the spectral densities at frequencies 2 nu and nu will vary with frequency as. Okay, so we can solve this problem by making use of the results that we learned in Planck's radiation law. So the spectral density in the frequency range from nu to nu plus d nu, it's given by the expression u nu d nu, that is equal to 8 pi h nu cube upon c cube multiplied by 1 upon exponential h nu by kt, where k is the Boltzmann constant, minus 1 and then d nu. Okay, if you just take a look at this expression, because we have to determine the dependence of the spectral energy density, which is this quantity. Okay, then it depends upon the frequencies by this expression nu cube and then this the exponential factor here. Okay, so we have to evaluate the ratio at two different frequencies. So that means what I can do is, we can write here that the spectral energy density u nu d nu, it's proportional to nu cube and then divided by e power h nu by kt minus 1. Okay, so now we have to evaluate this ratio at two different frequencies, which is given by, so that means what we are supposed to do is, we are supposed to evaluate the spectral energy density at these two different frequencies u nu. Okay, and this is equal to
2 nu q upon nu cube, and then it's the exponential factor at two different frequencies. Okay, and this is equal to 1 first at frequency 2 nu, to 2 h nu divided by kt minus 1, and then divided by again the same factor, so it will come in the numerator, so that is equal to e power h nu by kt minus 1 divided by 1. Okay, so this can be further written. So this, the factor of nu, that will cancel with here with each other, and here you will have only numeral constant, because we have to simply determine the frequency dependence, so it will disappear. So 8 into then 1 upon, so this can be rewritten as the numerator, this quantity, this is equal to e power h nu by kt minus 1 and e power h nu by kt minus 1 and multiply by the e power h nu by kt minus 1. Okay, so this will cancel with this quantity, and this is basically a square minus b square, so a square minus b square, this is equal to a minus b into a plus b. So here we should have a positive sign with one of the term here. Okay, so this term will cancel with these will cancel with each other, so this is equal to this expression, I am rewriting this one, 8 and then multiply by e power h nu by kt plus 1 and its power minus 1. Okay, so if you just ignore the constant that's involved here, so the frequency dependence of the ratio of the spectral density at these two frequencies, so the result matches with the option B here, so therefore option B is correct here. Let's take a look at the next question. So this question appeared in IIT-JAM 2017 examination. The statement of the question is, consider a system of n particles which are obeying classical statistics, each of which can have an energy 0 or A. So we are given a system of n objects, okay, where each particle can have energy either 0 or A. Okay, the system is in thermal contact with the reservoir, which is maintained at a temperature T. So that means this system, it's also going to be at the same temperature T. If K is the Boltzmann constant, then which one of the following statement regarding the total energy U and heat capacity C of the system is correct? So we have to evaluate the total energy U of the system and the heat capacity of the system. So let's try to understand this problem first. Okay, so here what we are going to do is, we are going to make use of the partition function approach. So first of all, we are going to write the partition function for one single particle, and then we will extend the result for n particle system, because in classical statistics we consider the particle to be distinguishable. It's important to understand this point here. The n particles, we are having a system of n particles, and because it's given that the system of a classical statistics, so that means we can treat them as distinguishable. So for one single particle system, the partition function will be exponential minus beta and corresponding energy E. Okay, and this is equal to, because we are having only two level system, so this will be for the first term, this is exponential minus beta multiplied by 0, so that will give you 1 only. Okay, so we have 1, and then the second term, exponential minus beta E plus exponential minus beta multiplied by the energy. Note that here beta is equal to 1 by kVt, so we will put it in the expression that we obtained at the end. Okay, let's call this as equation 1 here. So this is our partition function. Now by making use of the partition function, we can evaluate the average energy, which we call as the average energy per particle. This is equal to minus curly beta of ln z1. So we are doing the calculation for only for single particle, and then we can evaluate the total energy for the n particle system. Okay, so ln z will be logarithmic of this quantity, so this is equal to minus curly curly beta and then ln of 1 plus exponential minus beta e. Okay. So now it's differential with respect to beta, and this is further equal to log of this quantity. So this is equal to minus 1 upon 1 plus exponential minus beta e and then curly beta of 1 plus exponential minus beta e. Okay, and this is equal to minus 1 upon 1 plus exponential minus beta e and then its differential. Okay, so this will further equal to exponential minus beta e and then again curly beta of minus beta e, so that will gives us minus e again. Okay, so this is going to be our final result for the average energy for particle. So E1 turns out to be equal to E1, this is equal to how much? This is E, because we are having a negative sign two times, minus and minus, that will become plus, and we are going to take it to the denominator. So this will be 1 upon exponential beta e. So when we will multiply 1 upon exponential beta e here, so this will become 1 plus exponential beta e, 1 plus e power beta e. So this is our the average energy per particle. Let's call this as equation 2. But now we have to evaluate the total energy for n particle system. So that is equal to simply the total number of particle multiplied by average energy per particle, and that is equal to n e upon 1 plus e power beta e. Let's call this as equation number 3. Now from here, by knowing the expression for the energy, we can evaluate the heat capacity at constant volume. Okay, so Cb, that is equal to du by dt at constant volume. Okay, let's move to the next page. Okay, so we have the expression for u. Okay, u, that is equal to Ne upon 1 plus exponential beta e, or you can write this as E upon kt, where k is a Boltzmann constant. Okay, so I call this as equation 3. Now we want to find out the derivative. Okay, so Cb, that is equal to du by dt at constant volume, and this is further equal to keep Ne outside, and then well, it's 1 upon 1 1 by x, so this will be minus 1 upon 1 plus e power e by kt and its square. Okay, and then further exponential e upon kt, and then again further e by k as it is, and then multiply by minus 1 by t square. Okay, so this is a final this is what we obtain after differentiation. Okay, so after rearranging all the terms here, so minus and minus, that will become plus, as we are having n e square upon kt square. Okay, so we can rewrite this as k and then n e square upon kt its square. So here we were having only kt square, so I am multiplying in the numerator with k and also in the denominator with k. So this is what we are getting, and then the remaining term exponential e by kt upon 1 plus exponential e by kt its whole square. So this is our final result. Okay, so if we take a look at the options, so here let's go back. So here option C, Okay, option C and D, they are identical, so therefore the correct options are C and D.
Next question. The statement is, an isolated box is divided into two equal compartments by a partition which is shown in the figure. One compartment contains a van der Waals gas while the other compartment is empty. The partition between these two compartments is now removed. Okay, after the gas has filled the entire box and equilibrium has been achieved, which of the following statement is are correct? Okay, so let's try to understand this problem basically. Okay, so I'm going to discuss here the behavior that is shown by the ideal gas also, and then we will compare the results with the real gas. Okay, so if we just consider that the situation that is described here. So now talking about the ideal gas first. Okay, so when suppose here we are in the first case we are having ideal gas. Okay, now when this ideal gas is allowed to expand into vacuum here, so initially here suppose we are having vacuum here and it's allowed to expand into vacuum here. Okay, now when this entire compartment is isolated from the surrounding, so here we apply the first law of thermodynamics, that is du, that is equal to dq minus dw. Okay, so here because it's isolated, so here dq that will be 0 and dw it's also 0. Now I'm talking about the ideal gas case. Okay, dw it's 0, though the gas it's expanding, but there is no interaction of this system with the surrounding, so dw basically here it represents the external work. Okay, so it's 0, so that means when we are talking about an ideal gas, so du it is equal to 0. There is no change in internal energy of the gas, uf minus ui that is equal to 0, which implies u final that is equal to u initial. So note that this internal energy it consists of everything. So I mean it's the sum of the all kind of energy terms here for an ideal gas, because it's known that the total internal energy of an ideal gas it's purely kinetic in nature. Okay, so that means it simply depends upon the temperature. So when there is no change in the internal energy for the ideal gas, so this implies that delta T for the ideal gas it's also 0, which indicates for the ideal gas TF equal to Ti. So there is no change in the internal energy, there is no change in the temperature for the ideal gas case. Okay, now let's try to understand how this problem differs when instead of taking ideal gas, now we are talking about taking a real gas. Okay, so this point can be understood both from mathematics point of view as well as qualitatively also. So the temperature change, because this process is also known as free expansion, and the corresponding temperature change it's measured in terms of Joule coefficient, which is given as mu j, that is equal to minus mu j, that is minus 1 by c. Let me just check. Yes, it's minus 1 by cv, and then T dp by dt at constant volume minus P. That's a Joule coefficient. Okay, so that means in order to determine the Joule coefficient, we need to have the information about the CV, and if the equation of state it's known to us, then we can determine the corresponding Joule coefficient. And if it's 0, so that means that will results in no change in temperature in that particular case. Okay, so for instance, for ideal gas, for the ideal gas formalism, here PV is equal to RT holds. So here dP by dt will be R by V. So dP by dt by dt at constant volume, so dP by dt at constant volume, that is equal to R by V here. So if we just plug in R by V here for the ideal gas, so that will give us RT by V, and RT by V that is again equal to P. Okay, so P minus P that will give you 0. So that means for ideal gas this is equal to minus 1 by CV RT upon B minus P, and that is equal to 0. So that means the corresponding Joule coefficient,
the joule coefficient for the ideal gas, it's 0. And so further, the temperature change from the joule coefficient, it can be calculated as delta T, that is equal to mu J dV from some temperature T1 to T2, because mu J is equal to 0, so that means delta T is equal to 0. Again, from mathematics point of view, again delta T is equal to 0 for the ideal gas. But now, because for the real gas, the equation of state, it's given by this equation P, that is equal to RT upon V minus V minus A by V square. So this implies dP by dt, because we want to evaluate this quantity, the joule coefficient, okay, for now for the real gas, okay, for real gas, or you can say the van der Waals gas, okay, that is dP by dt at constant volume, and this will be equal to R upon V minus V, okay, because the other term, this term will give us 0. It's going to be a constant quantity, okay. Now substitute this value in the joule coefficient. So joule coefficient comes out to be equal to, so mu J will be minus 1 by Cv T dP by dt. So T dP by dt will give us RT upon B minus B, and then minus P. T dP by dt at constant V minus P. So my P, we will substitute P is equal to this quantity here. So minus RT upon B minus B plus A by B square. So this will cancel with this. So ultimately we are left with minus A upon Cv B square. Now the temperature change when we are having the real gas which undergoes the free expansion, so delta T, that is equal to mu J dB from volume V1 to V2, and that is equal to minus A upon Cb from some temperature T1 to T2, and 1 by V square dB, and this comes out to be equal to, after doing the integration, this is equal to minus A by Cv into 1 by V1 minus 1 by V2, because it's a case of expansion, so V2 it's larger than V1, so that means this quantity 1 by V1 it's going to be smaller than 1 by 1 by V2, it's going to be smaller than 1 by V1, okay. So that means this the quantity in this bracket, it's going to be a positive quantity. So ultimately delta T, it is less than 0 because of this negative sign here. This is going to be less than 0. So that means T final, or you can say the T2, you can say T2 is smaller than T1. So this equation explains that whenever real gas, it undergoes the free expansion, there is no net change in the internal energy, irrespective of the fact whether we are talking about the real gas or the ideal gas. So the conclusions are, for ideal gas, under free expansion, so I mean we are talking about free expansion in both cases. For ideal gas, these conclusions are valid. Delta U is equal to 0 and delta T equal to 0. So that is U final equal to U initial and T final equal to T initial, okay. Whereas for the real gas, net internal energy change delta U, that is equal to 0. There is no change in the net internal energy. What? Delta T, it is less than 0, or you can say TF is smaller than T initial. So that means cooling takes place. So here this delta U, it's not 0, so that means that there is no total internal energy. It's fixed in case of real gas also. And the point is that the total internal energy, it can be considered as sum of two different energy terms, kinetic energy plus potential energy. And where the potential energy, it's because of the intermolecular interaction.
intermolecular interactions. And in ideal gas case, these intermolecular interactions they were absent. Okay, so that's how the combination of these two terms, because total the sum of these two energy terms, it's going to be constant all the time. But when the real gas it expands, okay, so this can be understood qualitatively with the help of this diagram. Okay, so here this is the equilibrium separation between the different gas molecule. Let's call this as R0, and this is the potential energy term, U potential energy. Okay, so when a gas expands, so the intermolecular separation it's increasing, and because when the intermolecular separation it's increasing, as we can see from this graph, the potential energy term it is increasing basically, okay, in this direction. And also when the intermolecular separation it's smaller than this equilibrium separation R0, then again the potential energy term it's again increasing. So to keep the total energy constant here, when the potential energy term it's increasing, so that means the kinetic energy term it's falling, its value will decrease. Okay, and the kinetic theory of gases says that the temperature it's connected with the kinetic energy term. Okay, so when kinetic energy will reduce, so that is directly linked with the reduction in the temperature. Okay, so that's how we can also understand this problem qualitatively this way. So therefore the conclusions are, for the question which is asked here, the final conclusion is that the total internal energy of the gas has not changed, okay, and temperature of the gas is decreased. So these are the right option here. So let us continue with the next question. So this is from Carnot cycle. So consider a Carnot engine which is operating between temperature of 600 Kelvin and 400 Kelvin. Okay, the engine performs 1000 joule of work per cycle. So let's first draw the diagram so that we can understand it easily. So we are given a Carnot engine which is operating between two reservoirs at temperature T1 which is equal to 600 Kelvin and the temperature of other reservoir that is equal to 400 Kelvin, and in between we are having a cyclic process. Okay, and the work output per cycle is W, that is equal to 1000 joule. Okay, and here let's say that during each cycle it is extracting Q1 amount of heat from the upper reservoir, and it is also delivering Q2 amount of heat per cycle to the reservoir at low temperature. So now we know that the efficiency for such a Carnot engine, it is given by, it is the work output divided by the heat input, and in terms of temperature this is equal to 1 minus T2 by T1. So because T1 and T2 they are given to us, so we can directly calculate the efficiency. So from here eta that is equal to 1 minus T2 by T1, and that is equal to 1 minus 400 by 600. Okay, so whatever number we are getting, it's okay. So 3 minus 2, 1 by 3. Okay, so this is equal to 1 by 3, the efficiency. Okay, now again we will make use of this expression to calculate the Q1. So that means the efficiency W by Q1 that is equal to 1 minus T2 by T1, which is nothing but 1 by 3. Okay, so from here we can calculate that Q1 that is equal to 3 times W, and this is equal to 3000 joule. Okay, so the correct answer is 3000 joule. So let's take a look at the next question. It's a NAT type question. The statement is, starting with the equation TdS is equal to du plus pdv and using the appropriate Maxwell relation along with expression for the heat capacity, the derivative dp by dt at fixed entropy for the substance can be expressed in terms of specific heat, density, coefficient of volume expansion that is beta, and temperature T. So for the ice the parameters, the value of the certain parameters it's given to us. Now we have to evaluate the value of dp by dt at constant enthalpy. So let's take a look at the equation that is given to us and then try to solve this problem. So we are given that TdS, this is equal to du plus pdv. Okay, so from this equation what we can do is we can write TdS by dt at fixed pressure, because somehow we have to we have to obtain the results from this equation, so that we can connect the given parameter. Okay, so this is equal to du by dt at constant pressure plus p dB by dt at constant pressure. Okay, and I'm writing this to be equal to dq by dt, that is at constant pressure, and that is nothing but that is heat capacity at constant pressure. Let's call this as equation 1. Okay, now why I'm writing this to be equal to the Cp, it's a heat capacity at constant pressure, and how this is equal to this quantity. Okay, so this can be understood as follow. So if you just take a look at the definition of the enthalpy, which is H is equal to U plus PV, and the Cp, this is equal to this quantity dq by dt at constant pressure, and that is equal to dH by dt at constant pressure, and that is further equal to curly T of U plus PV, and all at constant pressure. And when we take its differential of the enthalpy with respect to temperature at constant pressure, that's nothing but it's equal to this expression that we just wrote here. So that's why from this equation basically we obtain the basic definition of the heat capacity at constant pressure. Okay, so now we can further write, so we will make use of this definition Cp, that is equal to TdS by dt at constant pressure. So here this can be rewritten as I'm making use of the reciprocity theorem that I'm going to write. Let me write the result first, and then I will explain it. Minus T, okay, ds by dp, ds by dp at constant temperature, and then dp by dt at constant entropy. What I have done here is, so with the as I said, we use the reciprocity theorem, which says that dxy dy at fixed z, that is equal to negative of dxy dz by keeping third variable constant, okay, and then multiply by dz by dy by keeping the third variable constant. Okay, so we made use of this result here to write this. So that's why a negative sign appear here. Okay, so now here again we will make use of the one more result, which is the Maxwell relation. So by making use of the Maxwell relation, we can replace this quantity ds by dp at constant temperature, that is equal to dB by dt at constant pressure. Okay, but here a negative sign will appear because pressure and temperature, they are coming on the opposite side of the differential, so we will have a negative sign here. Okay, so by making use of these two results, we can rewrite this as, this equation can be rewritten as, so Cp that is equal to T dV by dt. Okay, so negative sign and negative sign, they will disappear, so that is equal to T dV by dt at constant pressure and multiply by dP by dt at fixed entropy. So now we have to evaluate this dP by dt at fixed entropy, so which implies that dP by dt at fixed entropy, this is equal to Cp divided by T dV by dt at fixed pressure. Okay, let's call this result as equation 2. Okay, so basically we are interested in evaluating this dp by dt at fixed entropy. Okay, now here this dV by dt, basically we will make use of the definition of the expansivity, which is basically beta. It's also given, so beta, that is equal to minus 1 by v dV by dt. It's an isobaric expansivity. Okay, so from here we can write dV by, so this implies dV by dt at fixed pressure, this is equal to negative of beta times v. Okay, now v can be rewritten as in terms of the given parameter, so this is equal to minus v multiplied by mass divided by density, because density, that's mass over volume, so that's how we rearrange this expression. Now by making use of equation 2 and 3, so dp by dt at constant entropy, this is equal to the Cp value, okay, Cp divided by T dV by dt, so divided by T, and then what is dV by dt equal to? So dV by dt equal to minus beta, so multiply by minus beta m divided by rho, and after rearrangements, this becomes equal to minus rho Cp divided by T beta multiplied by m. Now all these parameters, all these values, they are given to us in the statement of the numerical. So Cp, it's given to us, okay, and then rho value, it's also given to us, and then temperature, it's 270 Kelvin, and the beta value, it's also given to us, okay, and then mass is 1 kg, is it? For ice, if we take, because it's not specified directly, so then the point is what value we should take, and if we take m is equal to 1 kg, and then after substituting m is equal to 1 kg, okay, and then by taking m is equal to 1 kg, the answer turns out to be equal to dp by dt at fixed entropy. This turns out to be equal to, if you plug in all these numbers, so minus 4.65 into 10 power 7 Pascal per Kelvin. Okay, so if you just take a look at the, what is asked is, we are asked the value of the pre-multiplier, which is n. So therefore n here, if we just focus on the numerical value, so n will be equal to 4.65. okay, and this is the answer when we consider m to be 1 kg.